Hello, everyone. Good afternoon. Hi, my name is Mario Zen. I'm the VP and the GM of Lenovo CSP segment. Very glad to today we have a distinguished panelist to talk about the challenges of the thermal driven by AI. So let me introduce our distinguished panel. So we have Chen Chen, thermal engineer, computer hardware from Meta. We have Mike Sabato from solution architects of HPC in the cloud from NVIDIA. We have Vinod Kamath, distinguished thermal engineer from Lenovo. And we have Mark Luxford, technologist from theyve. So with the challenges of AI, the boom, onset of AI, there's been a lot of thermal challenges driven by increased electricity cost, the thermal capping performance, as well as a very important session is how do we run the data center sustainable. So I'm very glad we have those experts here today to talk about. We'll look back at the history, where we are, and with the most brilliant people in the industry talk about how to address those challenges. So first, Mike, you want to look back, help us to talk about the chip side from where we get here?
Okay. So if you look back over the last decade, if we were to do LLMs are all about creating tokens, AI tokens. So the amount of energy required to do a token on a Kepler class would have been 42,000 joules to get one token. If we look at where we're at today with Blackwell, it is 0.4 joules per token. So when people talk about, we're high energy, well, the watts have gone up, but the energy has actually gone down by 100,000 orders of magnitude. So think about that level of change, and that's just over a decade. Because that has gone down by so much, that is creating the boom for, AI is actually practical, or to do LLMs at scale is actually practical. So from a 10 years ago standpoint, we had a GPU with a die and had GDR memory next to it. Now we have moved to multiple dies inside of a package, many stacks of HBM memory, and it is a full end-to-end solution. With our acquisition of Mellanox a few years ago, now the fabric is so much of a piece of the puzzle. So all of this is to make AI successful, we have to make AI low energy. So starting with the GPU, it is all about communication within the GPU at low energy. So the dies are close together, the HBMs are close together. Talking to a Grace processor, that is a low energy interconnect between the GPU and the CPU. To connect to the fabric devices, whether it's a CX7 or a Bluefield, those are putting the right level of acceleration for the fabric. The fabric interconnect for the switches. All of this is an end-to-end, how do we lower energy? So because lower energy is done by getting close together, that is driving up the thermal density, which is actually making it easier to justify doing the water cooling. Water cooling is not a new technology. It was there in the mainframes 30, 40 years ago. It went away from a large segment of the industry. It's now coming back.
Thank you. So Chen, as one of the largest end user, can you talk about what challenges you're facing of deploying AI?
Sure. Yeah. I would say as a thermal engineer, liquid cooling is I'm very familiar with this area since I was in school. However, I really didn't have a chance to adopt it in my industry career until very recently when I'll say some very highly creative and capable company developed a new chip, developed a new cluster type of architecture to enable the AI workload. And that has been our main focus to enable us infrastructure as Meta. And look into this. In the past, we used to live with relatively lower power density chips, lower density systems, lower density racks. And we have been living in an era where highly efficient, almost require no water usage. And our PUE number are very great. Our CFM numbers are very great. And we are marching very steadily, confidently towards the carbon neutral and water neutral goals at the end of the decade. But with the new servicing hardware products and the infrastructure service to provide, it becomes much more challenging. And then we look into the options we have. And actually since 2020, we already foresee a pretty growing trend of the AI workloads, even before the Gen AI shows up. And we see that liquid cooling will be our solution to these problems and help reducing the cooling power consumptions, help us enabling higher density, higher capability product with lower water consumption, with lower power consumption. So that's where we are, and we have very steady and very solid plan towards enablement of liquid cooling, and we do want to work with community partners to enable it at the best quality and scalability.
Thank you, Chen. So, Bernard, as one of the most respected industry thermal expert, can you talk about from your 20+ years history of doing this?
Yeah, so the point, I guess, that Mike made and then Chang made as well is, right, the need for efficiency is critical in AI, where you have well integrated silicon, the power consumption is high. About 12 to 15 years ago, we began a journey to understand the ability to deliver energy efficient computing at scale. Transporting the extracted heat with liquid, water or glycol, is a more elegant and efficient way to do this, because rather than spend 10 or 20% of energy using air-cooled systems to transport the heat from the silicon, if you use fluids, you could use that at maybe just a few couple of percentage points. Further, you don't need to chill the fluid. That was a requirement to us in the x86 HPC space about a decade ago, and we learned at that time technologies that enable this to be reliable, resilient, and efficient. And we have been deploying these types of technologies in the high-performance computing space for a while, both at Lenovo and in the common industry. There are several examples of that. So as we have technologies that have proven themselves to be resilient, reliable, and efficient, so we are at this happy intersect to bring those technologies to deliver the performance and the value of AI by providing that energy efficient solution. So I think we are at this, sort of inception of more efficient computing, valuable AI enabled by liquid, and we see this trend just expanding into all areas of computing over time. So I think we are a great place to deliver that type of solution, and especially with standards enabled in the industry to leverage and efficiently utilize them.
Thank you, Manoj. And when we talk about liquid cooling, we always talk about from chip to chiller, right? And very essential part is the CDUs. And I think, Mark, nobody knows CDUs better than you. Can you share your perspective?
Thank you. So for us, there's two parts to this. There's the trends we've seen over the last 20 years, because of course we developed our first CDU for data center applications, and CDU being a critical part of the infrastructure, the bit that's closest to the HPC or the server. We developed in 2005 for IBM System X, which now of course is Lenovo. And predominantly, first 5 years, it was all for rear door heat exchangers, really. The enterprise Cool Blue, if you remember that. And that was because nearly all servers, even HPC servers, were still air-cooled, except for some of the mainframe System Z stuff. Then around 2010, 2011, we started to see more liquid-cooled servers, DLC, direct liquid cooling at the chip. And we started to apply the similar CDUs or evolutions of those CDUs from 2010 through 2015. Similar CDU architecture, similar materials to early HPC liquid-cooled applications. Then around 2015, 2016, we saw a bit of a change, really. HPC was really on the up for research, for universities, for medical, for all sorts of applications, and we saw Lenovo really leading the charge there with particularly warm water cooling. And we developed then, at that point, CDUs specifically for high-performance compute applications. And there were big differences. Materials, all stainless, had to be completely compatible throughout the fluid network. High degree of filtration, 50 micron at the time. We're now at 25 microns, of course. And that depends on the pitch of the skiving, on the cold plates and QCs, a number of factors. So, and now, you know, that volume, particularly in those HPC applications over the last few years that we've seen personally, Lenovo, HP, all of the HPC applications have been for us, doubling every year through to 2022. Then it's like the gorilla woke up. In 2022 to 2023, we began, having been involved in HPC, high-performance compute applications and liquid cooling for some time, some years, and having that sort of track record and background, if you like, working with these guys. We saw these inquiries coming for AI at scale with a whole new set of demands, not just fluid compatibility, all the engineering sort of geeky things, but all sorts of infrastructure, facility, environment. CDU's got to be on the gallery at 45 degrees C. I mean, all these other demands started coming in, redfish, communications, additional resilience and redundancy, and also bigger groups, bigger SFNs, bigger secondary fluid networks. So instead of being, you know, a room full of high-performance compute servers with 1 or 2 CDUs, we're now seeing groups of 1.5 megawatt CDUs, groups of 8, huge secondary fluid networks, huge capacity. So that brings a whole new load of challenges. But the sort of core deliverables, if you like, of a CDU are 2 things. Constant PQ, or flow pressure, and a constant supply of, you know, constant regulated temperature supply of water, or PG25. In my experience, if you talk about temperature, this is, now we come to the sort of future challenges. The desire of all of the chip OEMs is to see, you know, fluid temperatures increasing where it could be sustainable, low energy heat rejection, potential heat reuse. Everyone wants to see, you know, 40, 45 degrees C fluid at the server, secondary fluid temperatures. And, you know, that's fine. And Lenovo have really been the only ones, in my experience, having deployed and commissioned CDUs for 20 years. Lenovo is right there at the cutting edge of being able to make that work. 45 degree fluid at the chip, 55, 60 degree return temperatures, and it works on the Neptune platforms. We've seen it, you know, every week almost. Now, future challenges means that the pace, the pure pace, and the desire, particularly of the hyperscalers, to see AI at large scale, means that, and the generations that we see now that are coming in front of us of increased power, increased density, there's a bit of conservatism creeping in, and we're seeing the temperatures, specified temperatures, dropping a little bit, because I'm not sure anyone really knows where we need to be for some of the silicon that's coming in 2-3 years' time, whether it's single phase or 2 phase. That's still a little bit of an unknown quantity. What I'm seeing at the moment is single phase right through to 2027, probably, but we need to be researching and working on 2 phase, and we are doing it right now. Other challenges are, you know, if you hear numbers of NVL72, for example, at 130, 150 kilowatts per rack. We then go to 303, 606, even 1.1 megawatt per rack, albeit a wide rack. Another challenge is even if we're at 90% to liquid, you've still got 10% to air. What are we going to do with all that air? The velocity, if you think about the velocity through a rack, which is basically blocked with servers, and handling that and cooling it either at source with a, with the powerful RID or heat exchanger, or even in the environment, the room, that is going to be the next big challenge I see. Delivering, if we stay single phase, delivering more water at constant pressure, constant temperature, not such a big issue. But I see the air as quite a big challenge moving forward, and getting power to the racks. That's probably a big one.
Yes, thank you, Mark. I think thermal liquid cooling is definitely in the spotlight right now of the industry, with a lot of attention. And I think Mark mentioned a great point of the unprecedented pace because of AI and all the hyperscalers are driving the industry towards to. So talking about liquid cooling, the technologies there has been there a while, but we've never been at this pace and the scale before. So there's a lot of nervous and fear across the industry about how do we get it to scale and the reliability, serviceability. So I think we can maybe each panel that talk about it from given a time, maybe a minute and a half, talk about how you tackle those challenges driving from the innovation perspective. Maybe Chen, from you as an end customer.
Sure, I'll start. As an end customer, our biggest concern of liquid cooling enablement is the scalability, including if the ecosystem is ready to scale up so quickly to fulfill the hyperscalers' demands with such short time window, and getting some new solutions and technologies into the play. Also, it comes to the quality control, the reliability modeling, and the operation protocols. Can we well contain the failure blast radius of the leakage scenarios? And can we also follow homogeneous and reliable operational protocols to tackle those failure scenarios? That's a very complicated question, and fortunately, we have very capable infra foundation, design team, operation team, and also we have very capable partners in the OCP community that can help us foresee, define, and explore the better options to tackle each of the different scenarios where we productively and in high confidence. Yeah, I would say that's our strategy now.
Thank you. And Mike, you know the best of where the AI chip is going to, so can you talk about it?
And I think everybody has been touching on the right topics. It's, this is going to be the first big push, but as a community, we're going to come up with better ideas. So whether it's a two-phase immersion, whether it's a peanut butter and jelly, I don't know what it's going to be. Something that, we need to have the right standards in place so it doesn't turn the data center on its head too frequently, but to be able to innovate, at the rack level or at the chassis level, so that over time, whether there's PG27, that's two better than PG25. There's going to be something, and we just have to be prepared for those things. We're going to learn as we, figure out what blast radiuses are and how to process this. Some of my hot buttons are, I want to put in shunt trip breakers to make sure that we can turn things off and make things safe. So we need this to be a easy, friendly process and evolve to that point.
Yeah, to speak too easy, right, to continue that thread, what matters is we are all agreeing to the fact that liquid's going to be in the data center on the silicon. So to make it easy, what it starts off with is after the design phase, a manufacturing phase. You need to make sure that the liquid loop that you're building has been completely tested, well tested from the supplier side and at the integrator side. And that, I think, is a critical feature of the designs. So you do not want to find out about issues actually post-manufacturing, right? You want to see it in manufacturing. If there are any flaws in the manufacturing process escape, you have to catch them well. And then you have to be resilient in the design so that it's tolerant of failures if they were to occur. it is impossible to guarantee a 100% failure-free environment, but you want to take it to 99.79s in your manufacturing and capture everything out there. And I think designs, standards, material sets, like we want resilient, based on copper, you see a lot of it in the environment, right? And then the right material set and the right test processes, I think, are going to be essential so that all the difficulty is borne by the supplier so that the end customer gets a worry-free, error-free operation.
Yeah, thank you. Mark?
Is this working? So I think another big challenge moving forward is, or we're seeing right now, is pure capacity. So we've gone from making a few hundred CDUs a year last year, 2023. We're now building 150 a month in 2 factories and bringing on a third factory, and that's putting pressure on the whole supply chain, dual sourcing required, that sort of thing. So that's a big pressure with keeping up with the deployment of the silicon, is having the nuts, bolts, and pumps and heat exchangers to back that up and allow deployment. Another thing moving forward is going to be the capability with every new platform that gets developed, every server that goes out there, there's another few gallons of fluid going out there. And we need to bring up that global capability on managing the fluids in the secondary fluid network, also the primary side too. And that's about having the capability to test, knowing what to do in the first place and how to have dose with the right chemicals in the first place, but then how to maintain that. And it's all very well, deploying zillions of CDUs, being able to commission hundreds of secondary fluid networks around the world, but if you can't then manage it for the life of at least for the life of the servers, you're going to be in trouble. So we need to bring up that capability and dosing and testing at the same time. That's going to be quite a challenge moving forward.
Yeah, thank you. Thank you for all the panelists' input. I think besides the product innovation from chip to system design to CDU and to data center, it's definitely a joint industry collaborative effort to make this huge transformation. Liquid cooling has been there for a long time, but never been at this scale. Right? So this transformation requires from the end user side, from the leadership designer side, system engineering side, and also CDU, and plus all the suppliers partners. It's not only about the design, the technology, but also about the entire supply chain. How do we make sure it's scalable, and then how do we make sure it's serviceable, and how do we make sure that everything can run a more sustainable energy to support the future AI growth. So thank you again for all the panelists and the OCP for this great opportunity. And the last minute, I'm going to say Lenovo is a diamond sponsor this year. We have a booth at B36. Welcome to check it out. And we got a happy hour booked tonight and happy hour booked tomorrow. Welcome, everyone. And thank you again.